Okay, so there's our whiteboard. And let's see what we can come up with in terms of a sketch on this. So we need these two figures on here, and then we're going to rotate about the x-axis. So this way. Now, y equals 2x squared plus 1. That should be pretty easy for us to graph. Agreed?
Mm-hmm.
Because it's going to be a parabola. Where's my vertex?
At +1, just 0, 1.
Very good. So I need to come up to 0, 1. Put my vertex. I'm going to get a scale on here. Just a second. And if I were to put in an x value of 1, tell me where my y value is.
It'll be at 3.
It'll be at 3. Very good. And if I were to put in an x value of 2, this is going to end up where?
9.
At 9. 1, 2, 3, 4, 5, 6, 7, 8. Okay. We'll put 9 up there. All right. Now, I can use symmetry to get these points on, correct?
Yeah.
All right. And I could sketch this graph. Ooh, sorry. It is so hard to draw on this screen. Okay. Now, let's get y equals 2x plus 12 on here. And I'm going to have to extend this graph more, am I not?
Yeah, because we might not be able to do that with the scale that we have so far.
We might not, because that's actually going to be an increasing function. I'm going to run off the graph, aren't I? So let me do this.
Oh, it's positive 2x. Uh-oh.
Yeah, so here's what we're going to do. Yeah, if it had been a negative, we would have been in better shape as far as the graph went. We'll just revamp our scale so that instead of counting by ones, maybe we could count by something else.
By 2.
By 2s, that should probably help. So let's put, if these are, and let me stick one more tick mark here, okay? And let's say all of these are counted by 2s. So we know that we had a vertex at 0, 1. I'm going to put that point there. Since this is counting by 2s, now the x scale, are we going, we're still probably okay with the x scale as 1s, right?
Yes.
Okay, so we're going to go up from, put the point 1, 3, and then we said we had 2, 9, right?
Right.
2, 4, 6, 8, 9 is about here. And
symmetric points on the other side.
yes, we're going to get those points.
I think we might have to do 3 as well on the parabola.
So if we do 3 as well, that's going to give us 3 squared is 9.
18.
9 times 2 is 18, plus 1 is 19, right? So let's see, 2,
Oh, right.
4, 6, 8, 10, 12, 14, 16, 18. 19 is just going to be about there.
Yes.
2, 3 is over here. Okay. Something like that. Now, let's get our line on there. So since we know this thing crosses the y-axis at 12, 2, 4, let's see. Yeah, 2, 4, 6, 8, 10, 12. And our slope is 2. Then we go up 2 over 1 because we're counting with scale of 1 on our x's, right? Up 2 over 1. Up 2 over 1.
See, the intersection points of what's going to get messy.
Because this is our shaded region, right? That's going to be revolved. But those intersection points, if let's first talk about while I'm trying to get this sketch on here, you guys tell me, what do you think is going to be the method that we're going to need to use to integrate?
The washer. We have a little tiny hole.
Yeah, because it's rotated about the X.
Okay. So we're going to need the washer method, and that's going to mean, and I'm just going to kind of roughly sketch. I'm not going to do a fancy.
And Miss Bedford, these points of intersection can be found on their calculator because these are not going to be
Correct.
exact integer. So y'all can
Correct.
type in your two equations and go to second trace and go to intersection and find those two points of intersection.
So that's what I think would be the best thing to do in order to find these. So I'm going to pull up the calculator real quickly, just so we can see. All right. And so in our Y1, we're going to put what? Was it 2x squared plus 1?
What's our equation? Come on, guys.
Yeah, y'all help me out.
And 2x plus 12.
And then 2x plus 12. Oops, hang on.
Oh,
2x plus 12. Okay, and if I do, let's just set the window manually on this. I don't think we have to go all the way to -10. We might make it -5. And for an X max, what do you think? How far out? We'll leave it at 10 for now. That's probably a lot more than we're going to want. For our Y min, maybe negative, let's do 25. And a Y max of 25. Let's just see what happens if we set the window that way. Okay, so I can clearly see those intersection points on here. Agreed?
Yes.
Yes. So if we go to second trace and we choose intersect, what are we coming up with for our X value there? If we round 2 places to the right, be 2.90. If we go 3 places, it'd be 2.898. Now, since it's said to round our answer to the nearest hundredth, it's going to depend on how exact you want to be. Ms. Hyde, do you want to give any instructions regarding significant digits or?
Well, to the nearest hundred is fine. You might want to go 3 decimal places, but 2 decimal places I think is fine.
I think it will work out okay, and we're going to end up with more decimals than 2 at the end, and then we can round back to 2.
Right.
So if we go 2 places, we're going to end up with 2 point what?
2.9.
It's going to be
0.
Yeah, 2.90.
17.80.
And if we were rounding the y-intercept. Now, remember, because we're going to use the washer method, okay, we're slicing and we're rotating about the x-axis. We're slicing perpendicular to the x-axis, right? So what we're looking for now is going to be those intersection points in order to find our limits of integration. So do we even need the y values necessarily for that? Or do we just need the x's? Do you understand what I'm saying?
Yes, because it's just the area in between them.
It's just the area between them, and because x is our variable of integration, we need our limits of integration to be the x values. So we're going to have an upper bound of 2.90. Are y'all following what I'm saying?
Absolutely.
Okay, very good. Then let's do this. Let's go back to second trace and let's get what that lower bound should be.
Oh.
You already have it?
No, I said.
I bet we're going along the x-axis to carve out this washer.
And that's going to turn into what?
1.90.
Negative.
Negative
Negative.
1.90. Okay, so that's what we're going to use for our limits of integration. And yes, Kelsey, it is going to be messy.
Yes.
It is going to be messy,
And
but
that's why you thought it was long.
yeah,
Mhm.
and I think that's good that you asked about that, because we haven't done one other than this one where the only way you were going to get those limits of integration is really to
Yeah.
use the calculator. Okay, now let's go back, because we've talked about the limits of integration, and let's see if we can figure out how we would set up the actual integral. So talk to me about, if we're doing the washer method, we're going to have an outer disk and
Minus the
subtract the
inner
inner
disk.
disk.
Mhm.
Yes.
So what would you say is going to be our outer radius?
Y equals 2x plus 12.
Yes.
Good
Yes.
job. And what would be that inner radius?
The 2x squared.
2x squared plus.
Excellent. So we said from a negative 1.9 to a positive 2.90 will be those limits of integration. We have a pi, which we can kick out in a minute if you want. And then we're going to have the upper rate or the outer radius, which is the 2x plus 12. And we have to do what with that?
Squared.
Very
Mhm.
good. Minus
Your inner
the
radius.
inner
squared.
radius squared. And let me move this out of the way. 2x squared plus 1 squared.
Because this is like, can y'all hear me?
Yes.
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 This is like two separate volume problems. It's not.
24 times 2 is 48. So 48.
Okay. So do we want to finish this out, or do you guys feel like now that we've covered how to get the limits of integration and how to set it up, that you would know how to finish from here? Are you interested in seeing if the answer you have, Kelsey, is right, decimal wise?
So I have already checked the answer with
With the calculator?
yeah, and
Okay.
it seems to be right.
Let's do it, Miss Bedford.
Okay, so let's do it. So talk to me about what your next step would be.
Algebra.
Algebra. Square double square.
Square double square.
Very
So
good.
if it's okay, I'm going to come up here and we'll kind of sidestep. When we square double square 2x plus 12, it turns into what?
4x squared plus 48x
Good.
Plus 144.
plus
Plus
144.
144.
Good
That's
job.
the first one. And then we will subtract now square double square 2x squared plus 1.
4x to the fourth, 4x squared plus 1, and that's all oppositized. Or you're going to have the negatives going to carry through.
So I think I missed a term in there. You said 4x to the fourth, and then your middle term is
4x squared.
4x squared, and then you have your plus 1, and you're right. All those are going to get oppositized. So that's going to turn into, and let me just do this real quickly. That's going to turn into a minus 4x to the fourth, minus 4x squared, minus 1.
Yes.
And now we can go back, kick out our pi, have a negative 1.90 on bottom to a positive 2.90 on top. And what's going to be our simplified, combined all the like terms integrand? What would you
Negative
think?
4x to the fourth plus
Yes.
48x plus 143.
Okay, and
What
that's
happened to the x squared? What happened to the x squared?
very good. They
That's right.
canceled. So the negative 4x to the fourth plus 48x, and then what did you say happens with the 144 minus 1? Becomes 143, right? So far, so good?
Yeah.
Okay. Integration on this is simple, isn't it?
No.
All right, talk to me. What's it going to be? How do you integrate negative 4x to the fourth?
Negative 4x to the fifth over 5.
Very good. Negative 4x to the fifth
Mhm.
over 5 plus
48x squared divided by 2.
And 48x squared divided by 2 becomes 24x squared, right?
Yes.
Right? 48 divided by
Yes.
2 is 24,
Yes.
plus
143x.
143x. And this is the part that's a little bit messy. Now when we substitute in these values, you definitely want your calculator for this. Yes, ma'am.
All right, guys, what you got when you integrated the minus 4x to the 5th over 5 and so forth. Remember, we can type that in as y equals, and then we can type in our upper limit, go to bars, y bars, and choose that, and
Hang on
enter,
a
and that'll
second.
give her. Y'all remember that?
Tell you what, Miss Hyde, talk us through that. I'm going to clear this part out.
Okay.
And
What
we're
I'm
going to,
trying to- all right, so go to y equals,
okay,
and just type in what we got when we integrate, which is negative 4x to the 5th over 5 plus 24x squared, negative 4x to the 5th divided by 5.
yeah, I forgot, just a minute, let me put my parentheses around this. Second, this is so hard to see. Okay, there we go. Insert.
All right, negative 4x to the 5th.
Okay.
Close your parentheses.
I'm getting there slowly. Okay, close my parentheses.
It's okay.
Divided by 5.
Divided by
Okay.
plus 24 plus 24x squared
Okay. Minus
plus
140.
100. No,
Oh, it was
no,
plus.
plus 143.
Plus.
Oh, sorry. Okay. Plus 143x. Okay.
Now, and then you need to, if you'll erase y sub 2.
Okay.
All right, now go back, get out of that and go back to your home screen.
Okay.
All right, let's type in our upper limit, which is 2.90. And we're going to store that as X, your store key. Guys, remember your store key is on the left-hand side.
Right.
Store it as X.
X, yes, and enter.
Okay.
All right, now go to vars, which I think is vars, y vars. Go to number 1, enter on function, and choose y sub 1, enter, and then enter again. So the upper limit is 452.5.45, approximating.
Okay.
All right, subtract the lower limit. Now, guys, do we have our anti-differentiation function in there already?
Yes.
All right, now what are we going to type in? The lower limit separately. So we're going to type in negative 1.90.
Mm-hmm.
And what are we going to do with that quantity?
Store
Store
it
it as
as
X.
X, and then you find the.
Must hit enter.
Mm-hmm.
Where you go?
Tell me what to type. Bars.
Because you don't want to have to type in the whole equation every time. Go to y bars.
Hit enter.
Hit
Enter.
enter again. And then hit enter again. And that would be the lower limit of integration, negative 165.25.
And what am I supposed to do with these two values?
Are those what?
Subtract them.
Yes.
Upper limit minus your lower limit.
Mm-hmm.
So would it be okay to just do all that in the calculator, or do you want us to?
I think so.
Okay.
Wouldn't it, Ms. Bedford, on this one?
Yes, I mean, if you
Okay.
have written out, let me back up a second so you can see. If you have written out
The integration.
the integration, just like you see here. And then you want to give me your bracket and show your upper limit was that 460 or 452, whatever it was. And then, and then minus, and then give me the value for the lower. That is perfectly acceptable. Because that's just arithmetic. That's not calculus.
No. And I think that's why y'all were affected by this. I think you were expecting an integer number, perhaps.
Yeah. And Kelsey's right. This is one that you can check your answer in the calculator. So you want to double check, but hopefully we're okay with that one. And if I'm not mistaken, I think that's the only one on this assignment that was a little squirrely like that, where you had to get these decimal.
What do we come up with our final answer?
All right. Final answer was 617.70. Am I correct?
That sounds right. Let me go back and look.
Times pi. Yes, it's 452.45
yes.
minus plus 165.25.
Yeah, the minus.
Gives you 617.70 pi. Correct?
Units cubed.
Units cubed. Good job.
That was rough.
That one was rough. I mean, just because it was, the math was nasty. The arithmetic was.
Absolutely was.
But the calculus wasn't that bad. It was the algebra. Now, is there anything else from 6.1 or 6.2 you want to ask about? Are you guys ready to start talking 6.3?
Excuse me.
Any problem with the shell? Do you have a shell problem?
I know Sam Carter told me earlier that she got her homework done, but she did have her brother kind of help a little bit. Okay. How did everybody else do?
Just 6.1. I've done a little bit on 6.2, but I'm not done.
We probably
I do have a question. So some of them say it's the upper, or where is it at? Let me find an example. It's the, I can't find an example. It's like a right curve minus a left curve. How do you know when to do a right curve minus a left curve?
Number 6, we could do, Miss Bedford.
And that's on the same worksheet, right? That you're talking about, Miss Hyde?
Well,
or are you talking about
6? Now 6 is the height is the horizontal distance.
Okay.
We did work 6 together last time.
Okay. We could
Actually,
do
we
7.
did.
Now,
Yeah.
7 is about the y-axis, so that would be one where it would be top curve minus bottom curve for the height.
So do we need, okay, based on your question, Jacob, do you want help with something more like 6, which we did do last time, where it is that right curve, left curve thing, because it was a shell.
I've got one, Miss Bedford.
Okay.
I've got one, Miss Bedford.
Okay,
Number
which
21 on section 6.2, not 6.1.6.2, but the original 6.2 section, number 21. And we're going to do this with shells.
Let's do that. And this is 6.2 in the textbook. It says y equals the square root of x.
Mm-hmm.
We have y equals 0. We also have y equals x minus 2. And we're going to rotate this about the x.
But we're going to cut shells, which means we're going to be cutting parallel to the x. So the height is going to have to be measured off from the y-axis. That's where you'd have a right curve minus a
left
curve. Now just graph it like you normally would and then isolate and solve for x.
Okay, so let's get the graph on here. Y equals square root of x. That one's pretty easy to put on here, agreed? We've got 0, 0. Give me another point. What's another point?
1, 1.
1, 1. What else?
4.
4-2.
4-2. Okay, we'll see if we need more in a minute. We have y equals 0, which is which axis?
The x-axis.
Mm-hmm.
The x-axis, okay. And y equals x minus 2. Now, where would y equals, tell me how to graph that. Go where?
Go down below the x-axis.
Okay,
2.
so my y-intercept is at -2. My slope is
Just 1.
positive 1.
1 over 1, up 1 over 1.
There you go. Keep going.
Up over 1, up 1 over 1.
There you go.
Oh, okay.
Intersection's pretty easy, isn't it, guys?
Yes.
Yes.
Now,
And
where are your boundaries? Miss Bedford, I want them to see that. The 3 curves would be y equals square root of x, the blue curve,
right here,
y equals 0, which is the x-axis,
right here.
and y equals x minus 2, which would be which portion of the line? We would not include that section below, would we?
No.
We used it to help us graph the line, but it is not going to be part
Mm-mm.
Of our
of
volume.
what we need. So I'm going to go back and put it in just that way.
There you go.
Does that help?
Mm-hmm.
Okay, and this is rotated about the x-axis, which means if they hadn't told us a particular method to use, could we have used the disk method? What do you
Been
think?
difficult,
Would it have worked?
but you would have had to cut it off at probably x equals 2, because there would not be you'd have to do right top curve minus bottom curve for that from there on out.
Right.
Okay,
So you might want to do this with shells.
so let's do it with shells. So with the shell method, we know that volume is going to equal, we're going to use the formula 2 pi r h, and then we'll have our variable of integration, right? In this case, if we're revolving about the x, tell me if you can decide what should be the variable of integration. Do we need everything in terms of x or everything in terms of y? If we're revolving about the x, which way are we cutting?
Circular shells. So you're cutting through parallel to the x through with a cookie cutter.
So
Isn't it
that means, say that again.
Isn't it y?
It's going to have to
Yeah.
be in terms of y, right?
Because
So
your
to the
radius is getting
x-axis,
bigger
right?
vertically.
yes. Now, if I look at the equation that they gave me, it is y equals the square root of x. What am I going to need to do so I can use it?
So your radius is
in
going to be
terms-
wherever you are along the
You're
y.
gonna have to square both sides so you can get it in terms of x equals.
So y squared would equal
Show
x.
them the height, Miss Bedford. The
Okay,
height.
let's see if I can do it right this time. I've
No, you
studied a
didn't.
little
You did
bit
fine.
more,
No, ma'am.
and I'm hoping I haven't been on too many meetings to where I've forgotten.
I
So
understand.
my height, since we're cutting this direction, right?
Yes.
I would have to go all the way out here to this curve, but then don't I need to cut off this
The distance
mount?
right there.
Because all I really want is what's inside that pink shaded region.
Right.
So that's your right curve minus your left curve. Does that make sense,
Why?
Jacob?
Yeah.
Because that horizontal line parallel to the x-axis is the height at any particular value of y. And that's your x distance, which has to be as a function of y.
So we have adjusted the curve, the blue curve, and turned it into x equals y squared. Are we going to need to do anything with the green line? That came from what? Y equals x minus 2?
Yes.
Mhm.
Do I need to rewrite that as well?
And solve for x, guys.
Yes.
Yes.
So
Plus
x is
2.
going to equal
Y plus 2.
y plus 2. that's what I'm going to need. Now, what else are we going to need in order to be able to integrate? I think I can see how to get the shell height. What's going to be my shell radius?
What you said, Kelsey.
You said just Y, right?
Mm-hmm.
Excellent. It is just Y. And
There's no distance between our curve from our what we're rotating around.
say that
Well,
one more time.
I said there's no distance between our curve and what we're rotating around, what axis we are rotating from. Right?
No.
You are correct. How about
The
my
Y's the radius lengths are getting larger vertically as you cut through horizontal to the X, parallel to the X.
yes.
So that's why wherever you're cutting along the Y is your radius at that point. And your height is what? Going to be measured from the Y-axis, and it's always parallel to the axis you're rotating about on shells.
Yes. So I'm thinking in order to get this set up where we know we're going to have to get limits of integration, that's really the last piece of our puzzle that we've got to come up with. Do you guys already know what we need to put in as our lower and our upper limits?
What do you say? 2?
From 0 to what?
2.
2, yes.
Excellent.
Because
Because
you're gonna stop this cooker cutter action when you get to Y equals 2, because that's where the meat goes away.
very, very good. So we've got 2 pi. Now tell me how we're going to put in that radius. You said it was what? This is the simple one.
The Y.
The
Y.
Y.
Wherever you are along the Y, which
Now
is
the
changing.
the
Correct,
height is the
y'all?
one
Yes.
we've got to be careful with. So what needs to go in first? What would be the rightmost part of our
Linear line.
The
The
linear.
yeah.
And you're describing X as a function of
Y
Y.
plus
Are
2.
you not?
Yeah. Yes.
Yes,
So
ma'am.
Y plus 2 is going all the way out to where that green line is, but we have to do what else?
Subtract
The left curve.
the left curve.
Yes.
Very good. So we're going to
And
take
the
that,
distance to the left
subtract,
curve is minus Y squared.
and then we need our
Good
dy.
job.
Jacob, does that help as far as the setup now that we've gone through it?
Yeah, I was just confused on when to to use the right minus the left. Like I can understand the process of actually integrating. I just didn't know when to use the right minus left.
What we're looking at here, and I think the other example we did was the same way. It's ended up where they were shell method questions. We were rotating about the X, which meant as we sliced perpendicular, we were needing to get the distance measured off from the Y-axis to be our height. Now, that's, these two are very, very similar in terms of the setup. Basically, the idea will be if you've got a figure that it's a shell and it's set up this way and you're rotating about the X, then you're going to have to do that right curve minus the left curve to get your radius height. If you had a disk method that this was rotated about the Y, then your radius, you would have really a washer, wouldn't you?
Yes.
If it was rotated about the Y, it would have been a washer method. And so you would have had to do the complete outer disk minus the inner disk. It wouldn't have been set up like this one was, because it's not just the radius, the difference of the radii squared. You'd have to get the outer washer minus the inner washer. Does that make sense? Or the outer disk minus
So
the inner disk.
if it were the washer method rotated about the Y, then your outer radius would be Y plus 2, and your inner radius would be X equals Y squared. And it would be pi times outer radius squared minus pi times inner radius squared. But this is the shell method.
Yeah.
And if it's rotated about the X, every variable has to be either y or has to be in terms of y.
Excuse me.
That makes sense?
Yes.
Yes.
Okay. So that would have been the difference. It would have been set up that way if it had
If
been,
it were the washer method.
if it were the washer method going around the y. But if it's the shell method, you're going to have to do right curve minus left curve if you're rotating about the x-axis. Okay? All right. Anything else? Are we ready to start? Length of arcs.
Yay.
I think let's
Finish
do
this.
it.
You all can finish this, okay?
Oh, I'm sorry. We didn't finish it, did we? Yeah, okay, hang on. Let's go back and finish this thing. So y plus 2 minus y squared, we really don't need those parentheses. I'm going to get rid of those. Well, let me put back what else disappeared that I didn't want to. Y plus 2 minus y squared. Okay, what would you do now, guys?
Just integrate, right? Oh wait, do we? No, we haven't done that yet.
Take out your 2
we haven't
pi and
integrated
then
yet.
Oh, I'm sorry.
But
We have
we're going to need to do what?
put your y through the
Yeah.
We
Distribute.
do need to distribute through with that y. Can we also kick out the 2 pi?
Yes.
Yeah.
If you want to. And then we will integrate from 0 to 2. Now, when I distribute through, do you want to put this in descending order?
Yes.
All right. So what would you put as your first term if we're doing
Y cubed
and it's in minus
Negative.
y cubed? Okay.
plus
That one.
y squared
Plus y squared
Plus 2y.
plus 2y.
plus 2y with respect to y. Okay. Now can we integrate?
Yes.
Yes. So negative y cubed turns into minus y
To the fourth. over
Fourth divided by 4.
Plus
Y to the third divided by 3.
plus
Y squared.
2y squared over 2.
2y squared over
But
2
it's just
cleans
y.
up to just
Yeah.
be y squared. Good. And we'll evaluate this from 0 to 2. So 2 pi. Let's see if you can tell me what the upper is going to be. 2 to the 4th power is what number?
16 divided by 4 is just 4.
And there's
Minus
a negative
4.
in front of it, right?
Yeah,
So
negative
negative 4. 2 cubed
8 over 3.
plus 8 over 3. And then plus 2 squared is
4.
4. There's my upper. Well, this is kind of nice. What's my lower?
0.
All the way through, right? And what happens to that negative 4 plus 4?
Cancels.
Sure does. So what would be my final cleaned up answer?
16 over 3.
Yeah, I just have to multiply 2 pi times 8/3. That'll give me 16 over 3 pi.
Units squared. Cubed.
Units
Yeah.
cubed. Good job. Okay. 6162, we think we've got it, correct?
We do.
We do. Okay, so here's what we're going to do. We're going to go look at the note sheet, and you guys are in for a treat. Miss Hyde has some real world explanations that kind of make this thing come to life for you.
Okay, y'all gonna have to really pay attention on this one.
Bedford,
Okay.
since the curves that are throughout 6-3 are kind of weird curves, do you still want us to graph them?
On 6-3, we haven't yet talked about graphing. Okay, 6162, you have to graph. I haven't said you have anything you have to graph on 6-3. Okay.
We gotta look at the concept.
All right, just a second. Let me back up a minute. Okay, we're going to do it this way. Now can you see the PowerPoint?
Yes.
Yes or no? Can y'all see that?
Yes.
Okay. So we're just going to go through it this way. When we get something that's just very random, I mean, that does not look like any kind of function that we would recognize and have an equation for, we could still figure out a way to measure the distance or the length of the curve using calculus. It's some real world examples. I think in the past, Ms. Hyde and I have talked about, have you ever noticed the lines on, say, power poles? Are those things perfectly linear?
No.
Or is there a little bit of a
Yep.
sag in the line? Absolutely.
These kind of look like ropes to me. You know,
Yeah.
finding the length of a rope in any
Yeah.
shape.
In any shape. So let me just move forward a little bit. We're not going to talk about the parametric equations, but we are going to talk about the
Very important.
idea.
Mm-hmm.
Yeah, that think about it for a minute. If I have this irregular shaped piece of rope and I wanted to know how long it was, but all I've got that I can use to measure with is, say, a yardstick. Could I pick 2 points and get the distance between those 2 points?
Yes.
And then maybe take that end point, pick another one and get a distance. And I could do that and work my way around and get kind of an estimate of what the length is. Would you agree?
Yes.
Yeah.
Now, what would make my estimate more accurate?
If we could have the infinite amount of points.
Mm-hmm.
Very good. If I make all those little segments tiny, 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 okay? Now,
So we're
we know,
looking for the length of line segments, the distance formula.
So am I wrong in thinking almost like limit approaching? Like,
Mm-hmm.
no, you're
Okay.
not
That's what it
wrong.
is.
oh, okay.
You are
You're
thinking
exactly right.
exactly right. So that's kind of the general idea here is we're going to be looking at that, because think about it for a minute. You guys remember probably from, this was probably middle school when you used it for the first time. You remember the distance formula?
Yes.
You
Look
can
at that
find,
right triangle. Right
yeah,
triangle, guys.
it's
Mhm.
basically you derive it from Pythagorean theorem, because if we drew that right triangle, then this distance, our horizontal length between any 2 points, can be found if we square the distance that's the height, our delta y. If we square the difference between the x values, the delta x, add those together and take the square root. That's our distance formula. The square root of your x squared plus the square root,
Look at it,
or the
y'all.
square root of your x squared plus your y squared, right?
Pythagorean theorem. And the delta x and the delta y are just symbolic of the change in x's between the 2 points and the change in y's.
Okay. So, in fact, I'm kind of wondering, while I've got this up here, Ms. Hyde, would you like to give them your explanation as to how you can get a ticket if you pass a couple of highway patrol, but you really aren't speeding when you go past either one of them?
Okay, this is what I want you to do as I say this. So everybody watch what she's doing. You with me, guys? Are y'all with me?
Yes.
Mhm.
All right, so what you have are 2 points there. And we're drawing a line segment, which is the hypotenuse of the right triangle. Do y'all agree?
Yeah.
Now, obviously, the arc of that curve is not the same as the length of that line segment, L sub K. But if you could choose points closer and closer together, those lines, those hypotenuse, give you a closer approximation for the length of the curve. Now, we are going to show you that in a moment, but before we do that, we are going to have a replacement. We're going to have a replacement for something in a moment. So I want you to look at the blue curve. Would you think that blue curve is differentiable? Would there be a slope at every point from point 1, from P sub K minus 1, point to Miss Bedford, and the other point?
We'll call that point 2 up here.
Okay. Would you agree that there would be a slope at every point on that blue curve?
Yes.
All right, now if we connect those 2 points with a line segment and found the change in the y's divided by the change in the x's, which is what the legs represent, yes or no, would that be the average slope between the 2 points?
Yes.
Yes.
Now, hang on, right here. I got to get somewhere there is a theorem called the mean value theorem, mean meaning average. There is some point on that blue curve, Miss Bedford, if you drew a line that is tangent at that point, because the 2 points making that red line segment are really the 2 points making a secant line. Do y'all agree?
Yes.
That's a secant. All right, now come back.
Okay.
Find a point somewhere on the blue curve, Miss Bedford.
Okay.
Some point, such that if you drew a line touching the graph at only 1 point, the slope of that line at that instant would be equal to the average slope between the 2 points.
So it needs to be parallel.
Like a tangent?
Parallel, and there's your tangent line. Now, if your graph is continuous, is it?
Yes.
Is your blue curve, and is it differentiable? Which means you can find a slope value somewhere in between. The slope at that point on that orange tangent line has to equal the average slope somewhere. There has to be at least 1 point in between those 2 points where the slope of the tangent line, which is instantaneous rate of change, is equivalent to average rate of change between the 2 points. The secant line and the tangent line have to be parallel.
Okay.
Now,
so far are you with me?
Here is my example. You drive, you notice a highway patrolman sitting, and you are passing by, and perhaps you're not speeding. Perhaps you might be speeding 55 miles per hour, and I can't come up with the numbers right now because I don't have anything writing down. You go maybe 3 miles up the road, and there's another highway patrolman. Perhaps you were not speeding when you passed by the first highway patrolman. Then you started speeding, and then you slowed down because you thought maybe this is a trap. You went by the second highway patrolman, and you have slowed down, and you're not speeding. However, if you took the distance between those 2 highway patrolmen, would you agree that would be like the change in the x's, and divided by the change in time? It took you 4 minutes to get from one point to the other. And if they took that change in distance and divided it by the change in time, that would be like the slope of the secant line. And if that came out to be over 55 miles per hour, there must have been some time in between your passing the first highway patrolman and the second, where your speed was greater than 55 miles per hour. Because there's got to be a point on a continuous function, if it's differentiable, where the instantaneous slope equals the
average.
And that's how they catch you guys. And you will often see 2 police cars, and it doesn't matter. They don't have to come after you. First one's not going to come after you. But if you speed and then you decide to slow down, you might all pull off the road and stop a while. Because if you keep on going, they're going to use this mean value theorem. That's what that means. Okay, Ms. Bedford, that's all I've got.
I think that's awesome. So you need to be aware of that believe it or not, they may not be able to compute all the calculus themselves, but they know how that calculus has been programmed in order to tell when they clock you with radar. They also know the length of time it's been since you passed the first guy, and that will tell whether or not you were speeding.
So Ms. Bedford, could you write on there, change in y, delta y over delta x, which, guys, would be the slope of the secant line. So can you write somewhere delta y, delta y divided by delta x? Would y'all agree that's average change in y with respect to x is equal to F prime
because when we differentiate, F prime is what that allows us to find the slope at any point on the curve, right?
Oh my gosh, I'm tired.
Do y'all agree?
I thought I was the only one. I thought it was my internet.
Same.
So would there be a point? piece of one, what's wrong? And piece of where if you found the instantaneous slope at that point, that would equal average slope.
Yes, right?
So that relationship right there is your mean value theorem. Mean meaning
Right there.
average. There's a place where the instantaneous slope equals average slope.
Okay, so here it is written out for us, the mean value theorem. All right. Now, that's really kind of funny. Okay, so
multiply and just wait for y. Let's do that before.
yeah, let's do that. Let me hang on a second. I'm going to pull up the whiteboard because I think it's going to be easier to see it on there. So
I'm going to use this relationship in a minute, guys.
all right, so delta y over delta x is equal to f prime of x. And if I remember Miss Hyde correctly, she would say, this is now my daddy's problem, correct?
That's right.
We could cross multiply, and what would that give us? Delta y equals?
F prime of x.
Times delta x, right?
Yeah.
Okay.
Yeah.
Now, talk to me just a little bit about what we said the distance formula was.
How do you find distance between 2 points?
The change in x is squared plus
Yes.
the change in y squared, all that square rooted.
Yes, because it's really what? The Pythagorean theorem, and you're finding
Right.
the length of
We're
the
finding
hypotenuse.
c.
Very good. Now, look at this for a second.
Oh my gosh.
And if we go back up here, could we replace our delta y with what we just said delta y was equal to?
The delta x times f prime of x.
Yeah. So delta x squared plus, we're going to put all of this in place of delta y. So we're going to have delta x times f prime of x and all.
Both factors squared. I want to say something, Miss Bedford.
Yes, ma'am.
Sam Turner.
Yes.
Sam talking to me. Would this distance formula be a way of finding little tiny line segments between consecutive points on that arc, on that
Yes.
curve? And if you then found the limit of all of those distances as the number of what? Little line segments approached infinity?
Mm-hmm.
Wouldn't that be the definite integral?
Yes, ma'am.
What does a definite integral do? It's a summation. It adds. It's an accumulator. In this case, it's not accumulating areas. It's accumulating distances.
So really, if we apply that concept, once we know what we want to measure from, what our beginning point is, what our ending point is, our lower and upper limits, we can put, for now, we'll put indefinite integral, but we can actually put values on there to measure it, right?
A to B.
A to B.
We can put A to B right now. I think that sounds good. Okay, now look at what we have under this last integram that I wrote. Can I clean up the second part a little bit? How do you square delta x dot f prime of x?
Square double square.
No.
Be careful. That's just really
they're multiplied. I'm sorry.
Y'all
Oh, they're plus.
Oh my God.
That's my bad.
It's just the coronavirus talking, Miss Hyde. It's okay.
Come on, y'all. Don't do this.
So when I square this, tell me what I'm going to get.
You're going to get the delta x squared
Dot
f prime, or how would you put that?
Yeah, f prime of x squared.
Yeah.
Right?
Under a radical.
Under a radical.
Okay, I'm not hearing from some of y'all. Everyone in this place, all of wherever you are at your place, that is what? The change in the x's plus the change in the x's squared between 2 points plus the change in the y squared between 2 points. You know we cannot keep that delta x and that delta y. They're two different what? Changes. So Miss Bedford what? Took out delta y and replaced it with delta x dot f prime of x from the mean value theorem, and she squared both factors. Are y'all with her at this point?
Yes.
Okay, now I'm thinking it still looks a little messy, a little unwieldy.
Okay.
Can we clean it up a bit? What
And
do
it
you notice?
really doesn't look like calculus quite yet, but it
Not
will
yet.
get there.
So think for a moment, do you see what you might call a common factor? Because we have how many terms under the radical?
2. So
2.
delta x squared.
And there you go. The delta x squared is a common factor, right?
And
Yes.
it's going to still be under the square root.
And it is under the square root. Thank you. And after I factor it out, what will be my binomial that's left?
1 plus
F of x.
F,
prime of
F
x.
prime of x.
Yeah, 1 plus f.
And that f prime of x is squared, isn't it?
Yes.
Awesome. So far, so good?
Yes.
Yes.
So talk to me. Now I've got two factors. I've got my delta x squared
Put a big dot, Miss Bedford.
and a big dot because there's two factors there.
Jacob, I see you.
So what happens if we're taking the square root of delta x squared?
We just get delta x.
Yes. Facts.
On the outside.
Exactly. So here's what we have. We're going to have the square root of 1 plus f prime of x, and that has to be squared all under the radical.
Just the F prime of x.
Just the f prime of x. And when we undo the squaring of delta x from that square root, does it look a little more like calculus now?
Mhm.
Does that delta x,
Oh,
square root of delta x squared is delta x, but delta x, when we put it as a definite integral, becomes your little tiny change in x because you're moving from left to
Right.
right, and you're making those little line segments so small.
With respect to x.
Yes.
so here's what we just did. We came up with a method, a formula we can use to measure all of those little tiny segments so that now we can get the length of curves. Okay?
That's your length of the entire curve. Now you're not adding areas, you're adding what? Distances.
Mhm.
Am I correct?
Yes.
So
And
tell
what
me,
is that? Okay, go ahead.
I was just going to say, so tell me something then. If we're adding up distances, when we get to our final answer, what kind of unit will this be in?
Your distance is not in square miles, is it?
No.
It's not cubic either. It's what?
No. Just first.
Just
Just
unit.
first degree. It's
Yeah.
just a unit.
First degree distance.
Excellent. Okay. So let's go back to the PowerPoint.
There's your formula. You just did your formula with the highway patrolman problem. I'm telling you guys, it works.
Yeah, you got it. So
Don't we-
there's our length of the curve. Now, these were parametric and we're not doing
No.
but
Here we
this
go.
is what we just came up with, this 1 plus
Yes.
taking the derivative squared, and then we'll take the square root of that. Okay?
And we might say that you could be measuring x. X could be a function of y. So instead of dy over dx, it would be dx over
dy.
dy, and your variable of integration would be dy instead of dx.
Definitely
Not-
possible.
That's right.
Okay, so let's look at this example. Let's say this function right here, y equals 1/3 onto x squared plus 2 raised to the 3/2 power. We want to get the length of that curve from x equals 0 to x equals 3. Now I'm going to pull up the whiteboard. Yes, ma'am?
Yes, Miss Bedford, and this is what I think, Kelsey, if you're listening, what you might have referred to. Sometimes it's not that necessary on, as far as my opinion is, to draw the graph. Right, because some of these get a little bit more polar coordinate graphing.
What was our x values? X equals what? And x equals what?
I'm going to rewrite it for you so you can see.
Okay.
We've got y equals, oops, hold on a second. Y equals 1/3. Why is this not wanting to grab? Or it is wanting to grab instead of write. So 1/3. And then in parentheses, we have x squared plus 2 raised to the 3/2 power, and we're going to go from x equals 0 to x equals 3. Okay, so our length will be the definite integral, and I'm just going to write the formula first, going from a to b of the square root of 1 plus f prime of x squared with respect to x. Does that
Now
make
that's
sense?
just f prime of x. Now, Miss Bedford,
Yes.
that f prime of x is the one that is squared. So it kind of looks like the whole thing is squared. Can you go back under the radical?
Let's do this. Let's take,
Yes,
if I do that, that looks better, doesn't it?
yes, yes, yes.
Okay.
Yes.
Yeah. Okay. So now that we've got that, what are we going to need in order to be able to plug something into my formula?
F prime of x.
There you go. So they gave me y, which is the same thing as f of x. Now let's see what happens if we differentiate that.
Oh my.
What will
Yes.
Throwback.
Yes.
Roll.
So I still have my 1/3 scalar, but what's going to be pulled down?
Now we're, hey, may I say
uh,
something? May I say
3/2.
something? Stop. You're not integrating. You are differentiating. So it's just
Yes.
the old power rule. It's
Yes.
actually the chain rule. You're differentiating here, which will then go into your integrand,
Mhm.
guys.
So
Okay.
let's actually do the chain rule. I'm going to go ahead and put 1/3 something to the 3/2.
Jacob Blackwell,
Yes.
something.
And our something is x squared plus 2. Okay, so you were telling me, Eli, we're going to pull down the 3/2.
Mm-hmm.
And then our something is going to get raised to what power?
3/2.
Guys, what are you doing when you're differentiating?
1/2.
Come on.
1/2.
What
Oh
half?
yeah, because you.
One hand.
Take
You
away 1,
subtract.
right?
Because you're
Yes.
differentiating.
And that x squared plus 2 is what's in here. Dot differentiate x squared plus 2.
2x.
Good job.
I agree.
Okay, so let's do a little cleanup. These are all dotted together, correct?
Our
What
3's
happens?
cancel
3's
there.
cancel.
Our 2's with the 2 and the 2.
Yes.
Mhm.
This 2 can cancel with this 2, and I'm left with an x, and then I can either leave it with the fractional exponent, or could I also put it under the radical?
Mm-hmm.
Whichever way you prefer. Okay? So x onto the square root of x squared plus 2 is going to be what I get, when it's differentiated.
And that x squared plus 2 is your radicand. Both of those terms are under the radical.
Okay, so let's go.
Now, Miss Bedford, what is that?
Yes. Where?
X onto the square root of x squared plus 2 is your f prime.
Mm-hmm.
Now look at your formula for finding the length of the huge arc.
You square
that row.
I'm going to have to do 1 plus, what am I going to have to do with this derivative?
Square it.
Square it. Now, if you want to, could we do this off to the side and then plug in? You can if you want, or you can plug it in and square it. If I square it,
It's
then
the square root.
let's see what's going to happen here. Notice there's not a plus sign. This is one term. There's 2 factors. So each one has to get squared, right?
Mm-hmm.
Separately.
Separately. So tell me what this is going to turn into.
X squared, and then just x squared plus 2.
Yes.
X squared onto x squared plus 2, right?
Is she right, y'all?
Yes.
And then dx. Okay, now we haven't put limits of integration on. Do you know what those are? Look at what they gave us at the beginning of the problem.
X equals 0, x equals 3.
There you go.
0 to 3.
0 to 3. So far, we okay?
Mm-hmm.
Yes.
Okay, so let me erase
We got
this.
to clean this up. You got to keep on with us.
Okay. So what do you see maybe we should do next?
Distribute your x squared.
X squared, yeah.
Good. So let's do that. We're still going to be integrating from 0 to 3, we have our radical 1 plus,
Plus x to the 4th
uh-huh,
plus 2x squared.
uh-huh.
Oh my. Now don't even think about it.
Now,
You can't separate terms under a radical, can you?
No.
no,
All right.
but here's the key to this. If you end up with something that looks like this, first of all, think about putting it in descending order.
Mm-hmm.
And if we do that, our only hope really is if it turns out that this might be a binomial that was squared.
It's x squared plus 1.
Yes, but you can't, guys, you cannot take the square root of terms.
No.
But you can factor it.
Mm-hmm.
So we can double check, is x to the 4th a perfect square?
Yes.
Yes. And is 1 a perfect square? Yes. And if we multiply, if we were to take the square root of each one and double it, would it give us the middle term? We have
X squared plus 1 is our.
Is what was squared.
Mm-hmm.
and now the
You just left
radical
it.
is going to cancel out the square. Yes, ma'am.
Unless you cancel out that radical, you're going to have horrible time integrating this.
Yeah.
But once you write this in, factored form under the radical, the square root undoes the square. That's why, look at that trinomial. X to the 4th plus 2x squared plus 1 is a square of something plus twice something plus the square of something. What was squared to give x to the 4th is x squared. What was squared to give 1 was 1. Do y'all agree?
Mm-hmm.
1 times x squared double will give you 2x squared. Did that turn into a perfect square trinomial?
Yes.
Which you
Yes,
then can, all this is algebra.
Factor.
Yes. Now,
So now the square root cancels out the square. What are we left to try to integrate?
Just x squared plus 1.
Just x
Which is
squared plus
easy.
1, which is easy.
Easy money.
So as long as we don't lose ourselves on the algebra to get here, this is not too bad. So tell me how that integrates.
X cubed over 3 plus
X.
good job. From?
0 to 3.
0 to 3.
And what is that adding up, children?
Distances.
Yes, all those tiny little distances.
Very good. So we're going to plug in our upper limit. 3 cubed is 27 over 3 plus 3 minus what's going to be our lower.
Just 0.
0.
It's just 0. 0 plus 0 is 0.
Mhm.
And 27 over 3 is?
9.
9.
So 9 plus 3 is?
12.
12.
12
And that's
units.
not pi because we're not dealing with
12
area.
units.
That's
And
just
just-
12 miles.
12 miles
12
or
meters.
12 feet or, yeah,
I
something
need
like
me
that.
some
Would that be
chewing.
the exact length of that strange rope-looking curve?
Yes.
Arc length.
This isn't
Good
that far.
job. Okay. I think we've got one more example we're going to do, and then we'll be through with our examples that are in here. Just kind of FYI, we talked last time about there would be a quiz coming up this next week. And the plan is I'm going to send you guys, I'm still trying to decide on the format, but basically I'm going to send you a take-home part of the quiz that you'll have a time window that you've got to do it and send it back to me. And then we're going to set up the Zoom meeting where you'll do probably maybe one problem for me in the Zoom meeting. And then, like, I know KP is working. I'll check with everybody else to see if I'll schedule maybe 2 times. That one time during class and then a time in the evening if somebody wasn't available for class. And we're looking at potentially being able to test with a third-party proctoring service called HonorLock. I'm experimenting with a student in a different class this week, and if it works well, we may do that for testing, at least for the final exam is what I'm thinking. So I'll keep you guys updated on that. That's why I was sending out those messages about what to do, what you had access to. Okay?
The email?
Yes, that
Okay.
email.
I was just wondering what that was.
Yes, that's what it was. I'm trying to get my testing options all worked out. So,
Now, you better tighten your seatbelt on this one.
okay.
It's not going to be hard, but we can do it.
Yes,
Now,
ma'am.
X equals kind of tells me that I'm going to look at X as a function of Y.
Mm-hmm.
So I'd really be measuring off what X is from the Y axis. Y'all
Right.
agree? So
Mhm.
instead of F prime of X, it's going to be F prime of Y,
Y.
because X is defined as a function with Y, or it's going to be dx over dy. F prime of
Exactly.
Y.
So let's see if we can figure out what F prime of Y would be.
Can I say this, Miss Bedford?
Yes, ma'am.
Children, kids, listen to me. Listen to Miss Bedford. When you're doing this, the first step is to differentiate your function. Square that, and then put it in your what definite integral that represents the length. Okay?
Okay.
Mm-hmm.
So,
All right.
two terms. We know we can differentiate term by terms. Tell me what you get when you differentiate y cubed over 3.
Y to the 4th over.
No,
Be
no,
careful,
you're
don't integrate.
differentiating. You're
Oh.
Y
differentiating.
squared, just Y squared.
Just y squared, because the 3 pulls down, cancels with the 3 in the denominator, and we end up with 3y squared over 3, which is just y squared.
Almost there, y'all. Come on.
Plus,
Be careful on the second term.
be careful on this. In fact, would it maybe help if I rewrite this?
Yeah, bring Y to the top.
Y over
Mhm.
4.
1/4
Okay,
of the
so
scalar.
let's,
Oh,
yeah, let's rewrite this as y to the -1.
Is that
So
right, y'all?
now,
Mm-hmm.
when you differentiate, it turns into what?
-1y to the
Negative
-3.
1 over 4. 1 over 4 Y squared.
Because I'm
No.
subtracting.
Well, but tell me what you're doing. You're
Oh, well,
differentiating.
it'd be
Y,
Plus,
Y to the -2.
yeah, Y the -2 will be on top. You're going to bring it to the bottom. Is that correct?
yes.
Yeah.
Mhm.
So that's going to turn it into y squared on bottom.
Mm-hmm.
Okay.
And then
And
we just formula now.
well,
Well-
before we go to the formula, should we do something else to this? Because when it plugs into the formula, we actually, do we just want the derivative, or do we need to do something else to the derivative?
Look in your formula, guys. Square.
Yes.
Oh,
Remember,
I guess. Yeah.
formula is the square root of 1 plus, and then we take f prime of y
Yes.
squared.
Why? Because we're going around the Y, dy. Is that right? dy is on the outside.
Oh, yes, thank you. Okay, so let's do that. Let's square this thing.
Now, how are we going to square this binomial?
Square, double square.
Square, double square. I want her to rewrite it as -1 over 4y. There you go.
Okay, and we're going to square it. So
Now, here's where you have to be careful.
what happens when I square y squared?
Y to the 4th.
Now, watch this one.
Now multiply y squared over 1 times -1 over 4y squared.
The Y squareds cancel,
Yes, they do.
but we have to double it.
Mm-hmm.
We'll
So
have
what
to
do you get?
double
What
it.
do you get when you multiply that? Y squares cancel. Do you get -1/4?
Yes.
And when you double it,
-2/4.
negative.
So just 1/2.
Okay.
Okay, so here's what I've written out. This is basically what happens when we multiply first term times second term, and then we'll double it. Okay, so you said y squareds cancel. Y'all agree?
That's how you do it.
Yes.
All right. Then what do you have?
I've got 2
And a 4.
on top and a 4 on bottom,
Cancel.
and then there's a -1 on top. So would you agree at this point we've got y to the 4th minus 1/2?
Yes.
Now, how much of the square, double square have we done?
Just 2 parts of it. Now we
Just
need
square.
to
We
do
did square
Double.
and double.
Now
we
what-
use square.
Square again.
Yes, so we're going to have to take that negative 1 over 4y squared and square it. So when we square it, what is that going to turn into? First of all, squaring a negative turns it into a
Positive.
positive
So positive 1
Positive
on top.
1.
over
16y to the
Y to the
4th.
fourth.
Yes.
that is going to be what my derivative squared is.
Can we
And
go ahead and factor it if we can?
Well, wait,
Not
because
yet.
that's going to go under
Right.
the radical.
if we factor it, we'll go straight back to where we were here.
Mhm.
Oh,
Okay.
that's true. Never
Yeah.
mind.
We put it
So
in the
let's do this.
equation now.
We're
Yes.
going to put it into the equation, which
Now
would
watch
make
this.
it 1 plus,
Plus.
and then we'll have y to the 4th minus 1/2 plus 1 over 16 y to the 4th. I could put that in parentheses, but since there's a plus sign there, it's not necessary. I've got a dy on the outside. I haven't put on the limits of integration, but I'm ready to do that. What is that going to be? From
1 to 3.
1 to 3. And what is the only thing under the radical that can be simplified or combined?
The 1 and the 1/2.
Would
The
that be a
negative
good
1/2.
1/2.
Yes, and it's going to turn it into,
Just 1/2 positive.
okay, so what I want to do is put that as my middle term.
Mm-hmm.
I want my y to the 4th first. I'm going to put my plus 1/2 because a positive 1 plus a negative 1/2 is a positive 1/2 plus 1 over 16 y to the 4th. My dy is on the outside.
And I want to know if that trinomial under the radical looks like something squared. First term is something squared. The third term is something squared. And the middle term might be the product of those doubled.
What we squared, except for it's not -1 over y.
No,
or y
go back.
squared,
Go back and look at y to the 4th. Tell me what was squared to give y to the 4th.
Y
Y
squared.
squared.
Write that underneath, Miss Bedford, kind of like
Yes,
a.
ma'am. Y squared gives us that. What
And
would,
all right,
Negative
that's what we.
1/4 y squared.
Now go over to the third term. What was squared to give 1 over 16 y to the 4th?
Negative.
Not
Y.
negative.
well, not
Oh,
negative.
just okay. 1/4
1 over,
Over 4
4 y squared.
y squared. Y'all, if I double square, I need to know what I squared and squared, don't I, y'all?
Oh yeah, if it was negative, the middle term would be.
Okay,
Yeah.
now how do you know what we're trying to make is a perfect square trinomial?
Mhm.
What was squared to give y to the 4th?
Y squared.
y
What
squared.
was squared to give 1 over 16 y to the 4th?
1 over 4 y squared.
Can you multiply those two together and double the product and get that middle term? Can you multiply y squared over 1,
I'm going to come over here. Y squared over 1
which is what she wrote below that y to the 4th? Can
times
you
1
multiply that
over
by
4y squared.
what's going to cancel?
Yeah, the y squared.
And then I'd want to double it. I
Y
want to
squared,
see if that's going to equal my middle term.
Yes, it
Yeah.
does. Yeah,
It
the y squared
does, because the
cancel.
y squareds
2 and 4.
cancel. The
And we're
2,
trying to get back to
2
factored form,
times.
guys.
Yes, it works.
It does work.
So how
what,
can we rewrite that radicand now?
The y squared plus
Mm-hmm.
1 over 4 y squared.
Squared.
Now, that's the key. If you can't get back to a binomial that's squared in factored form, you've had to have made a mistake somewhere along the way.
That's right.
Okay, that's your checkpoint. Whatever terms you have after you've done 1 plus the derivative squared should give you something that is factorable as a
Perfect.
binomial that will be squared.
That's right. That's right.
Okay. So now we still have not integrated, have we?
No.
No.
And we're
Why
still
do you
not yet
Why do
ready.
you think we wrote that as the square root of a quantity squared? A square root of a quantity squared.
Because that was
does
our
square-
formula.
Yes, but why did we
It
take that
does-
radicand on the inside, those 3 terms, and make it become a binomial squared?
Because the square root undoes the square.
Because the square root undoes the square, and it will just be not under a radical anymore, and it can be integrated easily.
Yes.
So we just have to integrate y squared.
Squared plus 1 over
Plus
4 y
1 over
squared.
4 y squared.
And if you want to rewrite it at this point as 1/4 times y to the negative 2 to integrate, that is perfectly okay.
Okay, so in this particular integration problem, you have to both differentiate,
Mm-hmm.
do a lot of algebra, and then end up integrating because of the formula.
What you're integrating should integrate pretty easily. It's the algebra to get there that's the mess. Okay, so I'm going to move on up to, in fact, let me do this. I'll change it.
Almost there, y'all. Come on, stay with us.
Hold on. Okay, so let's come up here. And I think we're ready to integrate. So tell me what we're going to get. Integrate y squared, it turns into?
Y to the third over 3.
Yes.
Mm-hmm. And then what about this 1 over 4y squared? We can think of it as 1/4 y to the negative 2. Integrate that for me.
It turns into 1/4 dot negative 1 y to the negative 1.
Okay, how do you integrate 1/4 y to the negative 2? Do you add 1? Divide by the new exponent.
Which is going to be a negative 1. So that's going to be a negative 1 over 4y.
Yes.
Where did the y come from on bottom, y'all?
From the y to
from subtracting your.
Well, it was y to the negative 2, and you added 1 to integrate, so it was y to the negative 1 on top. We're going to move it to the bottom. Is that correct?
Yes.
Okay, and this has to be evaluated from 1 to 3. Sorry, I keep trying to go up too high. I'm going to have to quit that.
It's okay.
Okay, so let's get our upper limit. That's going to be 3 cubed over 3 minus 1 over 4 times 3 is 12, right? Minus, now this one's not 0, so we've got to plug in. What are we going to get?
1.
Okay, so 1/3 minus
1/4.
1/4.
Oh, right,
absolutely.
Okay.
You can find the common denominator.
But
yeah.
Just
now let's go ahead on this first one. 3 cubed is 27, and 27 over 3 is what?
9.
9.
Yeah.
Minus 1 over 12. And then if I'm looking at, would you guys agree 12 looks like a good choice for a common denominator?
Yes.
I think so too. Do you want to go ahead and change 9 over 1 to be?
Yes.
Okay, so multiply 9 times 12 and we get what?
108.
108.
108 over 12.
Good job.
Minus 1/12. And then let's go ahead and change these. 1/3 becomes
12. Oh, 4 over 12.
4 over 12. And 1/4 would become
3 over
3
12.
over 12. So 4/12 minus 3/12 is
1/12.
a total of 1/12 in this lower limit. So here was my upper minus my lower is 1/12. Can we put all that together? What would we get?
Yeah. 106 over 12.
106 over 12. I kind of bet that reduces a little bit, you think?
How about by 2 at least?
Yeah.
Yeah.
58 over 6.
I think it's 53, isn't it?
Oh, 53. Yeah, my bad.
Yeah, and I've run out of space, so I'm going to come over here and put 53 over 6 units and box it up. Just units. Okay. Calculus, not that bad. Algebra, a little hairy at
Mhm.
times. But if you
Mhm.
take your time, keep up with it, and remember your checkpoints along the way, that you should end up with something that would factor as a binomial square, you'll be okay.
Will we ever get one where it doesn't factor?
Not if you do it correctly.
Wait,
Now,
Miss-
you may get one, if this is Jacob, is this Jacob? It may be possible, there's one on the example in the book that you didn't have to do. Your quantity under your radical just became a single term that you could take the square root of, I believe. You didn't have to do the square double square. It is possible that could happen.
Yes, but if you end up with multiple terms
Mhm.
like we have here, then it should be a trinomial that will
Mhm.
factor.
Mhm. Mhm.
Okay?
Well, in fact, your radicand may not turn into a perfect square trinomial, but it might be two terms, and you could use a baby U substitution.
That's another possibility.
Yes, there's
Yeah.
a possibility, and maybe if that happens in your homework, go with it on there.
Okay, so if it's three terms, look to factor. If it's not three terms, then there is the option that it might be something that you can integrate with the baby U,
Yes.
or
Yes.
something else that would be simple like that. Okay, I think you've made it through the hardest part.
You have.
After this, the rest of this is kind of like the cherry on top.
Miss Bedford, can you
Yes, ma'am.
point to the L at the very first where you
This
your
one?
work there, right there. That's the
Okay.
key one right there. Now, if they're measuring off from the Y, it's going to be in, X is going to be in terms of Y. Everything is going to have Y in it. If you're measuring off from the X, everything is going to have X in it. That makes sense?
Yes.
Okay. All right. Well, as far as I'm concerned, we have covered lesson 3 now. I believe your homework is 1 through 11 odd. There's not that many because there's kind of a lot of work on each one.
Mm-hmm.
Okay.
Guys, you got to do it. You've got to do this.
So let's work on this next week. Probably Wednesday is when we'll use part of class time to do the quiz, the one problem on the quiz. On Monday, we will maybe look at, depending on, we'll either work on homework problems if you have questions, or we'll start on work. We may go ahead and do that. And then Wednesday, we could do the quiz and review.
Mm-hmm.
That's probably the best way to go with that.
Yes.
So not this coming week, but the following week will be our test.
Are we good?
yes.
Okay, guys, you got to work on this. This is not hard, but you've got to keep looking at your formula, because the first step is to find your derivative function and square it, and then place that into your formula for length. Does that make sense?
Mhm.
Yeah.
Okay.
You can do
Well,
it.
don't hesitate to send a message if you have questions, you need help on anything. Otherwise, stay safe, stay healthy. I'll see you next. Okay.
All right.
Thank you.
Alrighty.
We're
Thank
almost there,
you.
guys. Come on.
Bye.
We're
Bye.
almost there. Dylan, Grant, Eli, Kelsey.